How we doing? Getting into this chapter 10, trying to wrap it up here. Probably two more short lectures. So I also wanted to clarify a little bit more of what I was working on last time with this S and P mixing business, right? How the order of the 2 sigma g orbital switches with the 1 pi u. So I wanted to explain that a little bit better than what I did last time. So when we started this discussion, we were talking about how when we create, or when we start mixing rather, 2s and 2pz orbitals, that they make two separate sets, right? This set of when the 2s orbitals mix make the 1 sigma g and the 1 sigma u, and this set when the 2pz orbitals mix make the 2 sigma g and the 2 sigma u. And of course, when you use the 2px and 2py, that's where we start making pi bonds, which you can see I've got right here on my Mathematica simulation. And what's important to note with these pi bonds, right, they're off axis, right? You can see there's this node in the internuclear region. All the same, there is still going to be some overlap with this pi bond and with this, where'd it go here? With this 2 sigma bond, right? There is still going to be some overlapping regions there. And so what ends up happening when you get into, like nitrogen and oxygen, for example, which is filling up, because it's half filled or more, you've got electrons in all of those p orbitals, which will then contribute not only to the pi bonds, but also this 2 sigma bond, okay? And so this is what I mean with S and P mixing, which is driving this 2 sigma to get lower and lower in energy as more electrons are populated in it, okay? And it's because of the symmetry about the z-axis. So as we start populating more electrons in that range, you've got a more symmetrical distribution around the z-axis. And you can see that as a huge effect of lowering the 2 sigma g energy, whereas the 1 pi u energy remains relatively stable. Okay, so I just wanted to clear that up. So let's get into heteronuclear diatoms. Okay, and so this is going to give us the quantum mechanic description of a polar bond. So a polar bond consists of 2 electrons and bonding molecular orbitals of the form psi equals some contribution of atom A plus some contribution of atom B, right? So here our simple molecule is, the molecule AB, right? We're just doing this generic, okay? And so remember, these coefficients here in the front, these give us normalization constants. And in the case of a basis set, like what we have here, right, the linear combination of 2 wave functions, these coefficients really are like a weighting scale, okay? So they give us like the weight that each atom contributes to the polar bond, okay? So in a polar bond, these 2 coefficients are unequal, right? There's unequal sharing of the electron. So the proportion of the atomic orbital A in the bond, right, is proportional to that weighting coefficient, and that of B is related to its weighting coefficient, right? So that's kind of just what I was saying there. So a nonpolar bond, of course, then would mean the 2 coefficients are equal, right? They contribute equally. And also interestingly, here an ionic bond, one of the coefficients is 0 and the other is 1. And if you think about which one of these has to be an cation or an anion, it makes good sense then that A here would be the cation and B would be the anion, because in this cation-anion system, the anion is in larger control of the electron. right? The cation has no electrons in its valence shell, or at least in its outermost shell, right? It's got, well, both have noble gas configuration, but the electron density is centered, we say, mostly on B, or entirely on B, okay? So, and the atomic orbital with the lower energy contributes the most to the bonding orbital, and the AO with the higher energy contributes the most to the antibonding orbital. So I'm just going to go through one example in full detail of this, and that's the classic, halogen, HF. We could also use HCl or HBr, but all of those molecules serve as really classic examples of how to start constructing a wave function of a heteronuclear diatom, and of course the description of a polar bond. So here we can see that right here, right? We've got the coefficients for hydrogen and the hydrogen 1s wave function, and the coefficients for fluorine and the fluorine 2p wave function, okay? And so as you might guess, this makes a sigma bond. So it's predominantly the F2PZ that's, I should really say FPZ, that's in charge, right? That's making the sigma bond. And so the way we start constructing not only these wave functions, but the MO diagrams is by first looking at the energy relative to its ionization limit, okay? So if we focus on just the hydrogen 1s, okay, this number, 13.6 eV, that actually comes from Rydberg's constant, right? So way back in the chapter 9, when we built up the hydrogen 1s wave function, and we described, this line right here would be the n equals 1 state, and right up here at the ionization limit, this would be in, equals infinity, right? So that's its full ionization limit, okay? And we could do the same thing for fluorine, right? Down here, this level, this would be describing the fluorine atomic orbital for not quite n equals 1, because this is the fluorine valence shell, right? So we'll say that for n equals 2. But then, of course, this is still the same reference situation as for the hydrogen, the ionization limit, okay? So fluorine requires a much larger ionization energy because it's more electronegative, right? As we remember from our Gen Chem days, okay? So this creates these first levels, which allows us to start to think about how to put together this solution, okay? And so now what we can see here, what ends up happening, so and I'm going to go through this in a little bit more detail next week, how we can start computing these energies. But effectively, what we're looking at here is the bound state for HF, okay? So down there would be the HF, that would be the 2 sigma G, okay? And then somewhere up here would be its anti-bonding orbital, okay, way up here. So that would be the HF 2 sigma U. And so we could then start to get at these coefficients by solving this wave function. So in other words, we would put this together as the Hamiltonian times psi HF is going to equal EHF, and then of course back to the original wave function. And so we would start making guesses at these parameters, not only to still satisfy the atomic energies, but also to solve for these coefficients. And so, and I'm going to describe that in a lot more detail in the coming weeks on a little bit of an intro into computational chemistry and how we can start solving things for complicated molecules. But effectively, what you can see, what ends up happening with this simple diatom, right? For the psi plus state, the hydrogen coefficient equals 0.24, and the fluorine coefficient equals 0.97. And so that's consistent with what we said Right here, the AO with the lower energy contributes the most to the bonding orbital. But now what ends up happening when you solve this basis set, right, for the psi plus minus, right? Because remember, when we, this is really, I should just say this is the psi plus state right here, right? To get that anti-bonding orbital, it would be, right, the psi minus state, right? Let's put that in so that we recognize that it's still connected to this generic example that I started by describing, psi A plus B, right? This is a perfect example of that. But you can see when these coefficients get, or when we solve the psi minus, the coefficients get switched, which is kind of cool. So now in the anti-bonding state, the hydrogen contributes the most, whereas the fluorine contributes the least. Okay, so actually I could say that's still positive 0.24. It's just minus the wave function, right? Okay, great. And so, like I said, there's a lot more complications into working out these energies and these coefficients. But what I want you to recognize for now, it starts by looking at the atomic energies and trying to solve for the energy by minimizing the energy of the bonding state. Okay, that's how this all starts, by minimizing the energy of the bonding state. Okay, moving on. So I want to get into molecular term symbols. And just like I said, if that wasn't clear, more on this in the coming weeks. A little bit of an intro into computational chemistry on complicated molecules.